All right, so day 17, we're back on the leaderboard. It looks like day 16 was pretty rough for a lot of people. A decent amount of people got it, but there are still quite a few that up until this point were doing every day and then didn't get to do day 16. I myself did not do day 16. I did not have the time to finish before I needed to do other things, so I will come back to that at some point. But today we are on to day 17. In day 17, we have a number of rocks, and this is basically Tetris shapes. They fall in order, so it starts with this one, that one, and then cycles through. The rocks don't have to spin, but they do get pushed around by jets of hot gas. So basically, this is like user input into Tetris, but you can only hit left and right. After a rock appears, it alternates between being pushed by a jet of hot gas, 1 unit, and then falling down 1 unit. If any movement would cause any part of the rock to move into the walls, floor, or a stopped rock, the movement instead does not occur. If a downward movement would have caused a falling rock to move into the floor or an already fallen rock, the falling rock stops where it is. So it only stops if it's downward movement that's blocked. So we get each rock starting at a certain position. We place it onto the grid. Jet of gas operates on it. Rock falls. Jet of gas tries to push the rock to the right. Nothing happens because it's at the wall, and it falls and it goes until it hits the ground, at which point it stops. And then we put the next one in and it goes down until it stops. And then we put the next one in, and these are all coming in 3 spaces above whatever the top rock is, and they all start 2 spaces in from the left. So I guess 0 0 for the rock formation here starts at 2 0 or something, or 2 whatever the height plus 3 is. So the height of this plus the height of the gap shows us a couple of the rocks falling. We're proving things to the elephants now. So they want to know how tall the tower gets after 2022 rocks have stopped, but before the 2023 rock begins falling. So we need this number for our test. We'll do ignore on test 2 as usual. For part 1, we've got, or let rock limit equals 2022. Then we need the rocks, which I think are going to be always the same. I don't think we get the rocks. Yeah, we just get the input. So this will be const rocks. Constants always need to be given a type. So we'll do a string slice and it'll be like this. So we'll need to parse the rocks into an actual thing that we can use. Ingor is not a word, so I'll change that to ignore. Okay, so we'll have like rocks on the rocks. Let's do the destructuring here instead. I like having the destructuring more than I have a random dot one over there. And then we'll have moves equals moves on the input, unwrap. So we'll have 2 parsers, one for rocks, one for moves. The moves one is significantly easier, so I'll comment out the rocks for now. So I'm going to make this a vec of moves. The moves are going to be an enum, left and right. We get a separated list 1 by line endings. No, not line endings, actually. We get a separated list 1. They're not separated, actually. So we get a many 1, and we have to parse alt tag. This could also be car. This car right past the input. These are going to be complete car to be specific about what we're importing here. Many 1 needs to come in. Alt needs to come in. We're going to map this into move left. We're going to map this into move right. And these closures do need to technically take an argument, so we're just going to ignore the argument. So now we've got moves. We've got a vec of left and right, which I find more readable. That's why I transitioned this into an enum rather than just using the characters, although using the characters for this, totally fine as well. So we've got the moves, can debug those out. We can't debug those out because I always forget to derive debug. And I am running check over here, but I want to be running test. So we get our list, right, 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 left, left, right. I have a hard time believing that this would have been a failed parse, but it's always possible, I suppose. And we'll debug rocks here. I feel like we have a couple of options here. We could try to do something very simple. We could try to just get the strings themselves. We could also try to parse these into maps themselves so that we have all of the positions, or do like a vec of vecs. That would also work. I feel like this is small enough that we don't need to care about really how we represent these. So maybe I do something like same kind of enum we just did, except this is called rock and this is called rock or gap. And then we don't even need to really worry about keeping these indices around or anything. We do need a function to do the actual parsing. So this is going to be rocks, and this is going to be a vec of rock. This is going to be separated list 1 instead, separated list by new line, new line. So in this case, because I'm on a Unix system, I'm just going to do new line, new line. This doesn't return the right stuff. So this is either going to be, we'll write this as many or separated list one, line ending, many one, and then we do the alt in here. And this is going to be rock, and this is going to be gap. So this can either be what? A vec of vecs of rocks, or a vec of, right? And then we do many one here. This needs to be tag. That's one of the problems. Of course, I'm going to put derived debug on rock formation, and we're not handling the error here. So right now we're ending up with a vec of rocks. And I just want to make sure that I don't do too many of these vecs here, I guess. So the first vec is a separated list. Second vec is also a separated list. So this here would be where we would need to map. Separated list by new lines. So that's why. That's why I wanted to pull this out, because the data structures make this a little bit easier for me to grok. We need a two-dimensional vec here inside of the rock formation. So all of this can go away. So we've got a separated list. We've got all of the gaps and all of the rocks over here in each of our formations. So like a 2x2 would look like this. So we've got a separated list separated by double new lines, and then a separated list for each line in each of the rocks that terminates in a line ending. And then we've got some number of rocks or spaces for each of them. So now we've got moves and rocks. So we need the field to be something. What does the field need to be? Or the playing area. The tall vertical chamber is exactly 7 units wide. And then we get the spawning conditions for each rock. So I don't think we need to specify the field as being anything in particular. Actually, let's make the field U32s, because I think it'll be interesting, because something just came out in the new version of Rust that I think I'm going to use here. So the field is a B-tree map of positions to, I guess, to rock. It would be a little weird to ship gaps in here, but it doesn't matter. Our logic will never put a gap in here. So we'll do B-tree map new, and we've got our field. We need to do a couple of things here, though. So rocks and moves got parsed out, right? And I'm going to change rocks to be rocks.cycle, or rocks.iter, sorry, .cycle. And I think I'm going to do the same for moves. So let moves equal moves.iter cycle. So now what we have here, if we debug moves.length, then we'll see moves length is 40. So what happens if we moves.skip 40, and then we debug moves.next? It's not mutable. And did we use it here? Yes. So let moves equals moves.skip 40, moves.next, and what do we get out? We get right at 41. So if we look at the move set, it should be right, left, left. So if we print all this out, we get right, left, left. And that's because we've skipped one full cycle, and now we're repeating again. So rocks.iter.cycle means that every time we need a new rock, we can just do rocks.next. Every time we need a new move, we can do moves.next, and everything works out for us infinitely. So our stopping condition is going to be the 2022nd rock after it's stopped specifically. So we either need a way to count the rocks that we're dealing with, or we can do a fold on rocks. So two options are like rocks.fold of some kind or something like that. Or we can do 4. So rocks stopped will be a U32. That's the number 0. And while rocks stopped is not equal to 2022. And then when we're done, we need to do field.iter. We need to find the topmost rock, right? They want to know how tall the tower will get after 2022 rocks have stopped. So just how tall it is field.iter, or rather field.keys.find or .map we'll do here. X, Y, Y .max .toString, and we'll unwrap this because it needs to exist. So we're finding from the keys, which are our positions, we're mapping, we're saying the max of the Y values, unwrap it, toString it. The other thing we could do is while let rock equals some rock, but that doesn't give us a stopping condition. So let current rock equals rocks.next, unwrap, and we get a reference to a rock formation. We don't really need it to be a reference, and we're going to drop it anyway. So 7 units wide, left edge is 2 units away from the left wall, and its bottom edge is 3 units above the highest rock in the room. Max rock height equals this, and this is going to be unwrap or 0, because it's either going to be the max of all of these values, or it's going to be the number 0. So we get a U32 here. We get the current rock off the rocks. So this is a U size. I'm going to do this as U32, and we're going to put the rock position 2 off of the side. So not 0, not 1, but index 2. And then we're going to put the vertical of the rock position the max rock height plus 3 for the gap plus whatever the height of the rock formation is. So it may just be useful to do a quick height, takes self, returns U32, and it's just self.rocks.length as U32. So now we have the rock formation height as an associated function, and we can do current rock.height instead of leaving it to be something else. That gives us a little bit more semantic meaning to the code that we're writing. So we do our setup here. We got the max rock height, we've got the current rock, we've got the position of the current rock, and then we need to apply the moves. So I'm debating how to do this. We could do this for a while let. We do need to determine somehow whether our rock in the next position collides with anything. But we do need to know that. So I don't want to really include that in the while let. So I think I'm just going to loop here, and we'll do moves.next unwrap. We can't use the word move, or we could theoretically use the word move if we did r hash, but I don't really want to. So I'm going to call it next move. Moves is probably going to be telling us that it's not mutable, so we do need to make it mutable. We need to make it mutable because next requires us to. So we grab the next move. We, of course, have to do something due to the next move, which is either going to be left or right. So current rock position. We'll do let next position was current rock position. Clone that, and then we just get to do next position dot zero dot the positions are where. I guess we don't really get away with being sneaky here, so maybe maybe I just won't be. If we're moving left, if current rock position is 1 or is 0, then we can't do anything. So it just doesn't move. So if current rock position dot 0 equals 0, then we have to return the current rock position because we can't move. Otherwise, we can do current rock position -1 and then current rock position 1, and that gives us the current position, which will give us, which is an I32 U32. Why is it not I32 U32? What did I mess up and where? That's the downside of letting it infer, is that you can get two different numeric types here. So it doesn't really matter for us, but I chose to type this as a U32 instead of letting it run. Now we need to do the same thing in the other direction. So this is 6, otherwise +1. I think that's right? I think they're 1 indexed. It's 7 wide and 0 is 0. So it has to be 6. Yes. So we get the current position, and then we need to try to drop it downward. So the next desired position is... So our desired next position is current position .0 or current position -1, but current position -1, as I believe we will find here, is that we cannot subtract an integer from the U32 here. Actually, this is .1. The issue is not that we're going to get a compile error specifically, but that this U32 that we have on the left, we're subtracting from, it could hit 0. But 0 is the level of the floor, so it would have to stay at 1. So actually, I think we're good. It doesn't matter. So desired next position is this, and then actually... this isn't equal 0, is it? This is like 6 minus the width of the rock, the max width of the rock. I think they're all squares. So square, 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 square. But what I mean by that is that if it's 3 tall, it's also 3 wide, and there is a rock in that position. So this is, actually that's not true for us. Okay, so what we need to do is have some max width. So fn max width, self, U32, self.rocks, .iter.map row.iter.filter, and we're going to filter any gaps out. .count.max unwrap, because this will always work. It's a usize, so we should probably just stick with usize at this point. I think anything that's a U32 can be a usize, and it doesn't matter for us for our calculations anyway, but it helps us out if we ever need to do any math that's big. So a usize, if you're not aware, is a platform specific sized unsigned integer. So on like WASM, this could be a U32. On my Mac, this will be a U64. It could also be larger on other platforms. I don't actually know if for us it actually supports any 128-bit kind of platforms, but like it could be a U128, but most of the time it'll be a U64. So if it makes you more comfortable to be specific, this can be a U64 in your code. Otherwise, you can make this whatever you want. So max width, and this is going to be 6 minus max width of the rock, of the current rock. And I feel like debugging this is useful, but I will leave that out for a moment because I think it's correct. Move right, drop downward. So for rock in current rock iter, or current rock.rocks.iter, we match on unless I typed something out wrong. Current rock.rocks.iter.filter. Why do I not get the type of R here? So vec of rocks. Oh, I can't match on a vec of rocks. That's why. Let's do enumerate. Then we get IR. We'll do a filter map, or let's do a flat map here. And this will turn into r.iter. This will be where our filter goes. So this is row. And this is me just calculating the XY position of each rock and then adding the desired next position to it. So we'll call those fragments. We'll say filter. This will be R. This will match on R. This needs to enumerate. So it'll be X. We get the rock, and this will be a filter map. And this will be sum. Up here, we'll take this Y, sum XY, or none. U size and a reference to rock. Why is that an issue? So we have closure may outlive the current function, but it borrows Y. We don't collect here, do we? I'm just going to collect into a vec of positions. So Y is borrowed here. In this case, since Y is borrowed and we have this filter map, we can just use the Rust compiler's suggestion. So closure may outlive the current function, but it borrows Y, which is owned by the current function. So Y is a reference into current rock. We could have a number of ways to deal with this. One of them is moving the Y into the closure using the move keyword. So now we've got a vec of U sizes. These should be, I think, added eagerly. So X plus, well, let's not add them eagerly. These are also numbers that we could calculate a long time ago too, and it might be worth it to do that. Right now we're calculating them all the time, but we don't actually need to. If we're going to calculate this here, this should be stored inside of that rock fragment. I'll leave it to do that. So we've got the offsets and we've got the desired next position. Now we'll do for position in fragments, or rather we can do fragments.iter.all, and all is going to be the position, which we are going to field.get the position. So I think we still have to special case 0 for the floor. Maybe we can just insert 0. So fragments.iter.all position field get position dot is none because we want it to be empty. Let can move downward equals this. If we can move downward, if we can move downward, insert set next position. Otherwise, we insert into field and we break. So field, we aren't doing the additions here. So it's position.0 plus desired next position.0, and then position.1 plus desired next position.1. And that needs to be a reference. So this is the position that we want to move each of the rocks into. We check to make sure that those are all empty in field, because they all have to be empty if we are going to move downward. So we can copy this logic here. If we have to insert, we do fragments.iter again. We have to do the same calculation. Let position equals this. Oh, actually, it's not this. It's not desired next position because we have to stick in at the position that we were at. So it's current position. This is if we can't move downward. Position.0 and position.1 were not found because this needs to be called position. And then this is field.insert key. And then this insert is always going to be a rock. And this is an issue because consider changing this to be mutable, mute field. So field isn't mutable. We scroll up, mute field. We still need to can move downward. So that's going to be current rock position. Current rock position equals desired next position. And then that should continue, right? This does need to be mutable. So where is current mutable? Attempt to subtract with overflow on 140. Current position .1 minus 1. We talked about this a little bit earlier. We said that one of the things that we could do is when we construct the field to insert the ground at 0 instead of doing some special logic. So we could do a simple loop here for I in 0.7. Let's make this X. Field.insert X 0 rock rock. And then we aren't bumping rock stopped ever. So we do need to do that. Otherwise this will never end. Wow, I wrote a lot of code for this. I'm going to need to do a refactoring video. This is the insert. And then we do plus equals 1. And we do rock stopped plus equals 1. And we end up with 4,636, which is wrong as far as I know. Okay, it is a day later for day 17 because I got pulled away while I was working on it. So it's time to go over the code that we have here, which has some interesting facets to it, as well as see if our part 1 response is even accurate. So one thing you'll see here is that I implemented display for our field or for our board or whatever you want to call it. And we are printing out how it looks at every step, basically. Every time a rock stops, we print out the board. I've done this in almost the same way that the problem shows us. The only things I don't have in our printout are the rock as it's falling. And one thing I have in addition to the rock as it's falling is I put in, instead of letting this rest at 0, I put in a bunch of rocks at 0. So the first thing is to set it to 2022 for the limit, because that's for part 1. And then we see that the answer is indeed correct. So the answer for the test is 3068, which is different than I believe I stopped at part 1 when we got our first wrong answer. At least stopped recording when we got our first wrong answer. So let's get the actual input before we start discussing the structure of the program. So I'll drop that into input.text. Again, it's just a really long line of left and rights. We can do cargo run bin part 1, and I'll throw a release on there. I don't think we necessarily need it. I'll throw it in there anyway. So it's saying 3153. I haven't put this answer in, so I don't know if it's correct yet, but it is, which is wonderful for us. That is a very large tower. So we'll have to check these numbers to make sure that they work for our I-64s or whatever. But let's start with the structure of part 1 and how it works. So let's do a recap here. We've got the rocks that we need to use to drop each rock. Each of those is a set of hashes or dots separated by 2 new lines. So we have 1, 2, 3, 4, 5 rocks here. For that, we build an enum here that is either a rock or a gap that represents either a hash or a dot. We also have this rock formation structure, which has each of those rocks parsed in vec, or rather a vec of vecs, and then also the position offsets. So if we treat the top left as 0, 0 up here, then we can work our way down the grid as like 0, 1, 2 or 0, 1, 2 to pick a point for each of the rocks. So offsets is just the rocks and the offsets from 0, 0 where they exist. We do implement display for rock formation. I'm not currently using it, so I won't go over it because I think it's pretty similar to stuff that we've gone over in other days in the past. And plus we have another display for the actual board that I'll go over in more detail. We have an impl on rock formation, which has height and max width. The height gives us the height of the sort of set of rocks. So if we look at this rock, it'll have a smaller height, and this rock will have a height of like 3 or something like that. So it's the, and this one will be like 4 or whatever. So we need that height to calculate how high to spawn in the original rock, because this is basically Tetris, right? The rocks spawn at the top of the board at a specific position, and then they drop down. Then we also have max width for a similar reason. We need to be able to move the rocks right and left in the board, but the board has a size, so it's only 7 cells wide, and we need this max width calculation to know whether we're going to hit the right-hand side of the board or not. So this is doing an iteration, mapping over each of the rows. Remember, this is a vec of vecs, and then we're iterating over all of the rocks, filtering them out, counting how many there are in each row, which for us, for the way that the rocks work, this works. The better way to write this would probably be to do an iteration over the points and get the largest X value. But we get the longest side. So that means that, especially in the place where we have a cross here or something like this backwards L, we need the count 3 for the width, not the count 1. So that's why it's called max width. We have our parsers. I think I went over the parsers in the other video segment, but we can do it again here. We've got a set of moves, basically, a moves parser and a rocks parser. The rocks parser uses the enum that we already looked at. We grab a separated list, separated by those double new lines. So inside of this, we're parsing each individual rock. Each individual rock is set up in a series of lines terminated in line ending. Each of those lines has many either hashes or dots. The hashes or dots we map over to turn into either a rock or a gap. And then once we get all of the rocks, we map over that parser and we turn it into a rock formation. We do the offsets calculation here. So we iterate over each of the vecs, each of the rows, as well as each of the columns, so that we get each of the rocks with the gaps filtered out, and we collect that into a vec of XY points. We do this here because we actually need this information at multiple times in process part 1. So it makes more sense to do it here since we don't mutate any of the rocks. we can just store this information in the rock formation and then use it later. Then we've got our moves parser, which is significantly simpler. It's just a many one, and it's either left or right, which we map over to mean left or right. This returns a vec of moves. You can either use car or tag here, it doesn't really matter. That brings us to the field itself. Now, when I originally wrote this, I used just this B-tree map, and I used that as the type in a couple of different functions. I realized that I would really rather have a type alias for this to represent the field so that I wasn't keeping it around. So there are two options for that. We can either do type field equals like B-tree map, whatever. This is okay, but if we do that, and I'll show you what happens if we do that. So if I actually type it out like this is called a type alias. And if I do cargo check, we'll see impl for type defined outside of crate. And that's because the type keyword doesn't create like a new type, right? It's just an alias to this B-tree map. So if we try to do an impl on this, it's trying to do an impl on the B-tree map. And you can't do that for a type that you didn't define. So we can't just randomly add functions to the B-tree map. Typically, if you want to add functions that operate on specific types like that, like iterator, for example, you'll find something like the itertools extension trait, which is a whole different pattern. So type alias isn't going to work because I want to add these associated functions on field, which means we have to use this new type pattern. And the new type pattern is just using struct field. It's a tuple struct, so it just has this B-tree map inside of field, and that's it. The only real difference here is that you need to do self.0 because this is the only element inside of the field struct rather than doing just self.keys or field.keys. There are ways to get around this. You can implement deref for the field and deref it to B-tree map. It goes back and forth on whether that's good practice or not. I think that there is something to be said for the ergonomics of this kind of being poor because you're thinking of this as field, you're not thinking of it as B-tree map, but you still want all the functions that B-tree map provides. So I don't know. Different projects choose to take a different stance on this. I've chosen to not implement deref for field just to make it clear. But projects like Bevy, for example, do offer their own actual deref derive that you can use. So this derive macro inside of Bevy allows you to deal with this. So this is a struct myNewType that contains a string, and then we wrap it myNewType string from hello. And here you can see that we're using the length function on a string, which bypasses or dereferences through the new type to string because we derived deref. So you can do that. I chose not to in this case. That said, field has a couple of functions that we do need. We need to get the highest y index for a rock at various points. So we go through all of the keys, which are a bunch of the XY points. We map over that to get just the Y values. We get the maximum Y value. And we either have rocks there or we set it to 0. If there are no rocks, the highest rock is 0. That's all that means. So normally unwrap would panic, but unwrap or allows us to set a default value. And this all returns a reference to a usize. So we dereference that to return just a usize. Can place rock at is something that we use in 3 different places. We need to do moves to the left, moves to the right, and moves downward. So can place rock at takes all of the offset points from the rock formation type, iterates over them, and then checks to see if any of them are currently filled. So I don't think I have one of the maps showing right now, but basically if you are dropping a rock in and you want to move either to the left, to the right, or downward, and there's a rock in a position that would like collide with yours, then you can't move in that direction. And all we're doing here is taking the desired next position that we would like to go to, adding the offsets for each of the rocks so that we get the actual position of each rock. And we're making sure that all of the positions, if we try to get them from the field, don't contain anything. So we use isNone. Then we've also got the display for field, and the display is really fun, I guess. I really enjoyed writing it. It's not particularly efficient or whatnot. It's just a display implementation that works. I chose to stick with display instead of debug because debug should still print out like all of the B-tree map points and stuff, right? But display should print out that pretty map. So again, to show you what we're printing out here, we're printing out something that looks like this with the lines on the bottom, the plus signs in the corners, the lines on the sides. We don't print out the top rock. We only print out this bottom field. So to do that, we get the highest rock, we get the Y range and the X range that we have to print out. In this case, the Y range is inclusive because the max rock height is a rock that exists. We have to go from top to bottom. So if you think about printing this out in order, you are printing it from the top left to the bottom right. and we're collecting this all into a single string. So we just go through all of these. So Y range, X range. So we are sitting at Y, and then we iterate through X. We iterate through each chunk. So we're going row by row now. We go into iter off the chunks, and we take each chunk, which is a fairly complicated type if you look at it. But what it means is that we have the Y and the X position in a vec. So we can map over each of the Y and the X positions for each row. We can translate them into either a hash or a dot based on whether we can get that point from the B tree map. And then we collect all of those into a string. So each row is now its own string, and we join those with pipe, new line, pipe. We stick that in the gap right here. So between two more pipes, one pipe for the start, one pipe for the end. And then we do a new line. Below that, we do plus on either side of 7 dashes. So that prints us out the entire board, basically. Which brings us actually to process part 1. Process part 1, we parse all the rocks, we parse all the moves. We want to iterate over each of the rocks and iterate over each of the moves because they all go in a cycle. So if we ever get through 5 rocks, then we want the 6th rock to be the first rock again. If we ever go through, I think we have 40 moves in the test input. If we get through those 40 moves, we want the 41st move to be the first move in the list. So that cycle will just infinitely cycle these iterators. We can just keep calling next. We don't have to worry about managing indexes or anything like that. Then we create our field, and that's just a field wrapping a B tree map. We insert the ground here. You'll see that the way I've written this requires that we have a ground here. There are some extra checks on, say, like line 247. If we go and look at that later, that will be if we can drop downward. And I'm doing a current position -1. So since we're using U32s, that can technically overflow. That's one of the reasons that we need this rock floor to pre-exist, but that's not like a hard requirement. It's just a way that I chose to do it. So we insert a rock by using field.0 to get to the B tree map. We insert at each of the X values at Y value 0 a rock. We need to keep track of the amount of rocks that are stopped because that will control whether we actually stop processing or not. The rock limit for the test in part 1 is 2022, and we can use a while loop. So while rocks stopped is not equal rock limit, we continue looping here. So this loop runs until this condition stops. Inside of this loop, we get the highest rock Y value from the field, and we get the current rock, or the next rock that we need to process from the iterator for rocks. We then set the current rock position because we need to spawn that rock somewhere in the board. That specifically is offset by 2 from the left-hand side, and it is the current rock height plus 3 plus the max rock height. So we've got the max rock height up there somewhere, right? Whatever the highest rock is. We need our rock to spawn in 3 spaces above that. But because we are using 0, 0 in the top left-hand side of our rocks, we also need to add the rock height to that calculation to properly put our rock high enough. So we've got our rock, and then we need to iterate over moves. So we get the next move from moves.iter. Loop is a keyword in Rust that will let us just infinitely loop until we want to break. So somewhere down here, there's going to be this break keyword, and that will break us out of this loop. When we break out of this loop, we'll end up iterating once again through this while loop, which will send us back into this loop and so on. So the while loop is letting us iterate per rock. The loop is letting us iterate per move. We then need to make either a left-handed or right-handed move. So we match on whatever the next move is supposed to be. If it's a left move, we do some processing. If it's a right move, we do some other processing. This processing is very similar. For the right-hand side, it's a little bit easier because we can do a +1, which will always succeed for a U32. So the next position that we want to be in is going to be the current position +1 on the x-axis. We can then test to see if the x value in that desired next position is bigger than the side of the board. If it is, then we shouldn't move, but it needs to be bigger than the size of the board minus the current max width of the rock. So if we have that plus sized rock, then current rock.max width will be 3, which means that the current rock position, that is the top left position of the rock, can't be more than 4. Otherwise, the rock will hit the side of the wall. So we check to make sure that it's not busting out the right side of the wall, or we make sure that the rock can't be placed in the next position. So we've got this can place rock that we talked about earlier. If we can place a rock at this position that we want to place one at with this rock, which has a certain size, if we can't place the rock there, then we'll return the current rock position. If we can place the rock there, we return the next position. And that's our left or right move. The only difference between left and right is this additional checked sub. So I chose to use U32s for the board size, and that means we can't go below 0. If we go below 0, a U32 will overflow into the U32 maximum value, which is very big. So the current rock position, .0, which is the X value, right? We set that up here. We do a checked sub with the value 1. So we are doing a -1 on the checked rock position value, but we're making sure that when we do that, it doesn't overflow or underflow. So if it does underflow, then we return none here because we can't do that. If it works, if it's fine, if it's like 5 minus 4 or something like that, or 5 minus 1 equals 4 instead of 0 minus 1 equals -1, then we get X position here. And we can use that X position in the same calculation that we just did for the right-hand side. If it's none, that means that this is trying to go more left than the left side of the board. So we return the current rock position there. So we either move left or we move right or we don't. And that gives us current position, which is NXY position. After we apply the left or right move, we need to do the same thing for downward. And this is another place where we could use that checked subtraction, but I chose to do it in the regular way. We check to see if we can place the rock, this current rock that we're working with, at the position that we would like to be in. If we can, then we set the current rock position to the desired next position, and we go through the loop again. If we can't place it in that next downward position, then we need to take all of the offsets for the current rock and insert them into the B-tree map because the rock is going to stop, basically. Once we've inserted all of the rock positions into the field, we increase the number of rocks we've stopped by 1. We break out of the loop, which sends us back into the while loop, and that will continue running over and over until we stop 2022 rocks. And finally, after we break out of the while loop, our program will continue past line 273. We'll get the highest rock Y value to string it, and that will be our answer. Okay, so with part 1 solved and recap, we've got to deal with this. The maximum size that can be in standard U32 max is only 10 digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got to do U64s at least. And this is going to be our number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13. Okay, so we should be able to make do with a U64. I have no idea how long this is going to take. This feels too easy. Let's see. Let's go for, this is the number we need, and this is our rock limit. And I think I'm just going to call this process because it seems like we're going to do the same thing. Rock limit, we'll make this a U32 because we're about to change everything to U64s. Input rock limit. Rock limit gets deleted there, so we can pass that in now. So for part 1, it should be input in 2022. So if we test that, oh, right. I have U sizes here. So we should be fine, actually. I'm going to change that to U size. I thought I used U32s, but I guess I swapped out. We do need to make this pub because we use it in our binary. So we do a cargo test. We get 1 passing test. So part 1 is still passing. So all we need to do here is grab this number, paste it in, and I am going to use the technique of using underscores. I think we have U64s because we're using U sizes. We need to not ignore our test. We run our test. We hope it passes. It occurs to me that I should have run this with release. So that makes me think that we need to take a different approach here. And it's nice to know that if you do cargo test and it does take a while to run the test, part 2 works has been running for over 60 seconds. We can get a print line going here. I think we can just cargo run bin part 2 release. And this isn't going particularly quickly, so it would take quite a while, actually. Right, it's only at 50,000 and we need to go quite a bit higher. So the way that I'm doing the problem is clearly too slow. So I let this run for a while just to kind of prove that it doesn't go fast enough, which was true earlier. Although I realize now that I'm going to cut that waiting out of the video. So, but we're only at 1 million. 1, 2, 3, 4, 5. Oh, 100,000, which is even worse. So I think realistically we can only go that far. And you see how long this ran for. I ran it for 5 minutes. So I think that there has to be something in the rocks and the moves and the cycles because the inputs and the rocks keep repeating over and over. So at some point those should line back up. And if those line back up at some point at the same spot, then we have a cycle in the sort of overall progress. So I'm wondering how to detect that cycle. So if we go down to rock stopped, we have the position of every rock that we're placing, and we have the position of like the top left of the current rock. I think that this is our solution here. Like we store the X values for the current rock, the X value and the rock type, and we store that into a vec until we hit something that that starts cycling, which could be a very long. And once we get something that starts cycling, I think we pop out into a second process. So we kind of need to keep the number of indexes around, or at least the height that gets added, and then we can just keep adding the height over and over until we hit the right number of rock. I feel like there are some loop detection algorithms in PetGraph, so we could build up that graph. I don't know how many times we would have to run the loop detection if we did that. So we would have a is cyclic directed G bool returns true if the input graph contains a cycle, but we also need to find that cycle and reapply it. So if I look for cycle in the search for PetGraph, we have a cycle error. That's a return value from something. That's an error. Negative cycle also. This is the only function that I see that is returning a cycle, like the cycle itself. 1, 3, 2. So yeah, I need to do a little bit more research to do the cycling, because the only way we're going to get to a tower this tall is going to be to find that cycle and then reapply it over and over. So I will see you for a day 17 part 2 video at some point. Hope you enjoyed part 1, and we'll get to part 2 soon. Have a great rest of your day.